The next talk is by Niv Haim, Vardi Gilad Yehudai Ohad Shamir and Michal Irani from Weizmann Institute. It's on reconstructing training data from trained neural networks.
Hi everyone, I'm Niv Haim, and I will talk about reconstructing training data from trained neural networks. This is our work that was published in the recent NeurIPS a few weeks ago as an oral presentation. It is a joint work with Vardi Gilad Yehudai, who are first equal contributors, and also Ohad Shamir, and my advisor, Michal Irani. I'll start with the motivating question for our work. Consider this neural network classifier that was trained to separate between two classes of images. For example, images of vehicles and images of animals from the C410 dataset. Given this trained neural network, will you be able to retrieve samples from this model just by looking on its parameters? In our work, we show that for some cases this is in fact possible, and the images in the dashed boxes are images from the training set that was reconstructed using our method. We do this by defining a loss function over the model and its parameters, where the optimization variables are the inputs to the network, shown here in blue. You may be familiar with such optimization methods over the inputs. For example, by maximizing the activation of the class score, such patterns comes out that resemble the training set. This shouldn't come as a surprise that such method reveals secrets about the training set. Talking about revealing secrets, similar methods were shown in the context of privacy. For example, model inversion by Fredrickson et al. Managed to reconstruct faces from a face detector, but this was done for a fairly restricted setup where each class corresponded to a face, and each face had only 7 images in the training set. And such activation maximization methods usually result with the images of the class average, as seen here. The nice thing about our loss function is that it is derived from a fundamental theoretical result. It was shown that for some methods, for some neural networks, by training gradient descent, the parameters of the model converge to a very specific solution, one that can be specified by a set of equations. Knowing this set of equations and the parameters of the model, we are only left with optimizing over the inputs such in a way that could satisfy this set of equations. This property is known as the implicit bias of gradient descent, and let me tell you a bit more about it. Empirically, it is known that neural networks are really great at generalizing to unseen data. This has puzzled theoreticians. Why, from the infinite solutions that can fit a given training set, neural networks converge to a solution that also generalizes very well? Sudri et al. Showed that logistic regression trained with gradient descent converges to the hard SVM solution. This is the classifier with the largest margin that is also known to generalize better. It was later extended to deeper homogeneous neural networks. By homogeneous, I mean a very large class of architectures that include also a stack of linear layers and Rayleigh function. This is very popular architecture. In our work, we focus on such binary MLP classifiers. Other than converging to a solution that generalizes very well, it also can be specified by a set of equations. So let's put it formally. A classifier phi with parameter theta trained on a data set of xi and yi will converge to this set of equations. Now, don't get intimidated by the equations. They are fairly complicated. But what we want to see here is that they relate the parameters of the models to the input data set. These equations actually come from the KKT conditions of the maximum margin problem. So we also get these extra parameters, lambdas. There are just scalar parameters for each training sample. Now, given this set of equations, if you believe the theory, you believe that your model converged to this set of equations, we are left with finding the inputs that would satisfy these conditions. For this, we define our loss functions. The first one is just minimizing the first condition. This is just taking the norm of the left-hand side. The other one is requiring that the lambdas would remain positive. And we have a very simple prior, just requiring that the outputs would be bounded between -1 and 1. The algorithm for reconstructing our training data is as follows. Given a train classifier phi, we initialize the optimization variables xi and lambda i's at random. We set the labels in a balanced manner, and then we just run the optimization process to minimize this loss. This is how it looks like. See how these inputs, in order to minimize our loss, slowly drift into samples from the training set. Okay, so at the end of the optimization process, we are left with many inputs. Some have more resemblance to the training samples, while others less. In order to evaluate how many training samples we managed to reconstruct, we take the original training samples and search for the nearest neighbors in the reconstructed samples. We do this using the structural similarity, which is a common method for comparing between natural images. So at the bottom row, you see samples from the original training set of the model. At the top, you see reconstructed, the best reconstruction for each of them. And here are some more. Let's talk about the numbers here. This experiment was done by training a 3-layer MLP. The training data was 500 images, 250 images per class, to solve the binary CFAR10 problem of vehicles versus animals, where the generalization accuracy was 80%, which is far from random. Now, see how the constructions really look like samples from the training set, like this car here. There are also some weird artifacts, like this reconstruction that was converged to an average of 2 samples, and in general, there are some noises that we do not fully understand. Here are the results for the same model and training set size, but for images from the MNIST, again, binary classification of odd versus even. A nice analysis showed that our results actually corroborate with the theory. If we look at the third condition, this object on the left-hand side is actually the distance of each sample from the margin. It can be either 1 or larger. If it is 1, it means that the sample lies on the margin. If it is larger, it means it is far from the margin. If we look at the fourth condition, this distance, if it is not 1, it means the sample is far from the margin. Its lambda I must be 0. Going back to the main condition, if I put it this way, we see that the parameters of the model are a kind of a weighted sum of something that has to do with the samples, very simple, similar to SVMs, if you're familiar with it. And these weights are these lambdas. So for samples that are far from the margins, lambdas would be 0, and the parameters of the model would not depend on the samples that are away from the margin. So we do not expect to reconstruct this. The way we visualize this is by taking for each training sample its best reconstruction from our reconstruction. We measure the quality of the reconstruction using SSIM, so higher means better reconstruction, and we plot this quality of reconstruction against the model output, against the distance from the margin. So we actually see this margin here, and what we see is for the best reconstructions are actually samples from the margin. We also see that there are a lot of other samples that are close to the margin that we're not able to reconstruct. And with this, I will summarize. So what we show is reconstruction of large portion of actual training samples from trained binary MLP classifiers with no additional information on the training set. This is motivated by the theory of implicit bias of gradient descent. And there's a lot to explore next. For example, going to realistic settings like convolutional neural networks or multi-class classifier, where we already have some interesting preliminary results. Going beyond theory, so these theorems that I've shown has some assumptions. It is interesting to see if we can reconstruct samples from models that didn't have these assumptions, and some of them actually work. This may imply that more interesting theorems can be proved. It would be really interesting to see if we could reconstruct samples for other types of data, like tabular data or 3D data. And in the sense of privacy, if we can defend against such reconstructions attacks. So thank you for listening, and for more details, you can visit our website.
Thank you, Niv. Questions?
Did you test the quality of reconstruction as a function of overfitting the dataset?
So how would you define overfitting the data set? Because what I say by overfitting is that we have low generalization accuracy. But what I showed is that for this binary classifier, the random would be 50%, and our models achieve 80%, which is far from that. Other this, you would have to somehow define what you mean by overparameterizing. So normally people speak about this getting low test error. It is interesting to see it. This is not what you asked, but thinking of overfitting. Sorry, maybe I missed your question. Did you say overparameterizing or fitting?
I did say overfitting.
Overfitting. Okay, sorry. So it's interesting.
Of course, in the sense that the error on the training set decreases, but the error on the test set or validation set increases.
Right. So the simple question is that we show that the test error in our case is not random. It's not the best, but it's 80% versus 50%. It is interesting to think of overfitting in the case of memorization in the input, like memorizing the data, but I think this is the first work that actually shows that inputs are memorized in the parameters and not memorized in the sense that the classification score is good on the training set, but not on the test set.
Any other questions? Okay, let's thank the speaker.
Thank you.
And